Hi there, Mr. Sutton here, bringing you the BC Calculus 8-2 Extra Practice number 3 solutions on arc length. For this problem, I want the length of this curve over the interval from 0 to 4. So first, let me get dy over dx, because I'm going to need that for my arc length formula. So that's going to be 3/2 x to the 1/2. And now I'm going to need the integral from 0 to 4 of square root of 1 plus dy over dx squared with a dx differential. Let me enter all this in the calculator now. To make things a little bit easier, I'm going to enter my dy over dx that I just figured out in y1, and then I'll quit out of there, and I'll do math 9 for integral. We've got 0 to 4. We've got the square root of 1 plus, now I have to do that function I just entered in there squared. So alpha trace y1, that's my dy over dx. Square that, put a dx, and press enter to give us approximately 9.073. On this problem, I'm trying to find the length of this parametrically defined curve over the interval from 0 to 1. So let me get my derivatives first, x prime and y prime. For x prime, using my power rule, 3 times a third is going to cancel. My exponent's going to be 1 less, so I just have t squared. And for y prime, dy over dt, this is going to be 2 times 1/2, which is just 1 times t to the first power. So entering that now in an integral, we have the integral from 0 to 1 of, I need the square root of dx over dt squared plus dy over dt squared with a differential of dt. And let me just use the calculator for that. So on my calculator, here's what it all looks like. We have integral from 0 to 1. We have our square root. This is really t squared squared, dx over dt squared. This one is dy over dt squared, which is just t squared. And I used x's for everything because it's okay as long as you use the same variable. Press enter, and that's about 0.609. For this problem, they want us to set up and evaluate an integral to find the length of this curve, which is defined in terms of y rather than x, so that's kind of weird. So in order to do this, we're going to need the derivative of x with respect to y, dx over dy. So using the power rule here, we've got, let's see here, 3 times the 3 down here is going to cancel, so this is just going to be y squared. And I can think of this next term as really being 1/4 y to the negative 1. The derivative of that is going to be negative 1/4 y to the negative 2. And now I need to integrate over the interval from 1 to 3 the following. So I need to use my arc length formula. That's going to be 1 plus the derivative squared inside a square root. So we have square root of 1 plus dx over dy squared. And make sure you have a dy for the differential because part of this was actually setting up the integral. But now that I've set that up and I've defined what dx over dy actually is, I can just use the calculator to do the rest of this. To make my life a lot easier, I'm actually going to define my dx over dy in my y equals as y1. And yeah, these variables here are y's, but I'm going to use x's because that's my input variable on the calculator. And it'll work out just as long as I use x consistently wherever y is used down here. So quitting out of there now, let me do my integral. So math 9 from 1 to 3. We need the square root of 1 plus, and now I need dx over dy squared. Remember, I stored dx over dy as my y1, so alpha trace y1. And now I can just square that, and this is so nice because I can do all of this stuff squared without worrying about parentheses or the rest of it. And now let me just do dx because everything I defined on the calculator was in terms of x. But as long as you're using the same dummy variable consistently, you're good to go. Press enter, and that's about 8.833 if we round that off. For this free response problem, it's your birthday, or somebody's birthday anyway. We have a baker creating a birthday cake, and the base of the cake is this R region in the first quadrant under the graph of y equals f of x. This is defined on the interval from 0 to 30, and here's what f of x looks like. It's just a piece of a sine curve, and everything is measured in centimeters here. Now this R region is shown in the graph up here, And they even give us the derivative of the f function, f prime. Now, we could have found this on our own pretty quickly, but they just saved us a little bit of time, which probably means they're going to make us pay for it somewhere down the road. So for our first task on this, we're told that the region R is cut out of a 30 by 20 rectangular sheet of cardboard, and we toss out the rest of the cardboard. We want to find the area of the discarded cardboard. How much are we recycling? So for that area, you can imagine up here that there's this 30 by 20 rectangle in which this R region is included. We just want to figure out basically if I take that rectangle and subtract away this R area, what's left over. So my discarded area then is going to be this 30 times 20 for the rectangle minus, and now I need a way of talking about the area of R. Well, for that I can just use an integral. I'm just finding the area under the curve of f basically. So integral from 0 to 30 of f of x dx. And they defined f of x up here. So once I've shown this, I can just plug it in my calculator and see what it is. To make this a little bit easier to do on the calculator, and just in case I need it again, I've entered the f of x function as my y1. I'll probably need to enter f prime at some point, but I'll cross that bridge when I get there. So quitting out of there, let me just write an expression here. So here's what I wrote so far off camera. I have my 30 times 20 minus math 9 for integral. We're going from 0 to 30. And again, I stored f of x as y1, so alpha trace y1. And then I'll put a dx in there. Press enter, and that comes out to about 218.028. And since the one-dimensional units are measured in centimeters, this is going to be square centimeters. For this next part of the problem, we're actually going to make the cake. The cake is a solid with a base of R. Cross sections of the cake perpendicular to the x-axis are semicircles. So you can think of this cake as being kind of a bunch of semicircles rising out of this base. Now, if the baker uses 0.05 grams of unsweetened chocolate for each cubic centimeter, how many grams of chocolate are we going to need? So basically, if you have this many grams per cubic centimeter, and you want to find out how many grams you need to figure out how many cubic centimeters you're going to need. So we need to find the volume of this cake, and then we can multiply whatever that is by 0.05. So to get the volume with one of these, we need to integrate some area slices over the interval from 0 to 30. So I need an area formula for those area slices. I'm going to call this a of x, and this is going to be my semicircle area. So if these are semicircles, that's going to be 1/2 times pi r squared, half a circle. But we need to define r in terms of the x here. We need r in terms of x, because this is an a of x function. So what is the radius of each of these semicircles going to be? Well, if the semicircles are going from one end of this bounded region to the other, that's the whole distance across the bounded region that this f of x function is giving you. This f of x function is giving you the diameter of the semicircles. But we don't want the diameter, we want the radius. So instead of r, I'm going to write 1/2 of f of x. And that'll give me just half the distance from one end of this bounded region to the other. So putting that in here, I'm going to have 1/2 times pi times 1/2 f of x squared. And I'm going to simplify that to be, let's see here, this is really going to be, we'll still have f of x squared, but now I'm going to have a 1/4 times a 1/2 times a pi, so pi over 8 times f of x squared. So I'm going to use this area formula in just a moment to tell me the volume. Let me get my general setup though. So my general setup, my chocolate's going to be, we said, 0.05 times the volume. So that's 0.05 times the integral now from 0 to 30 of my volume, which is just going to be a of x dx. Because we're adding up all these semicircle slices of delicious chocolate. Well, it's unsweetened chocolate, so I don't know really how delicious it is, but whatever. Let's do this on the calculator now. To reduce clutter on my calculator, I've entered my a of x function down here, this function right here, as y2. So this is going to be pi over 8, and y1 was f of x, so I can do y1 squared, alpha trace y1 squared. And now let me quit out of there, and I'm doing 0.05 times the integral, so math 9, from 0 to 30 of, now I need the area function, which I entered as y2, so alpha trace y2, and we'll do a dx there. So this comes out to 117 point, let's see, I guess 810 if we round to 3 decimals, and that's going to be grams of chocolate. For the last part of this problem, they want the perimeter of the base of the cake. So the base of the cake here you could essentially think of as just having two sides. You have this 30 side down here from 0 to 30, so we're going to have to include that in our perimeter. Plus, we have this curved side over here. Now, to find the length of this curve, we're going to have to use our arc length formula. So that's going to be the integral from 0 to 30 of, and now when I do this, I have to take the square root of 1 plus the derivative of this curve squared. So in this case, that's going to be 1 plus f prime of x squared, and I'll put a dx for my differential. And now I'm just going to do the rest of this on the calculator. So here I am again in my y equals. In the interest of, again, reducing clutter, I've entered the f prime function now as my y3, and I just used alpha y equals to get my fancy fraction mode here. So quitting out of there now, we've got 30 plus integral, math 9, from 0 to 30 of the square root of 1 plus, and now I have to do f prime squared. So remember, I stored f prime as y3, so alpha trace y3, and then square that, and then we'll put a dx over there. Enter. We have a perimeter then of 81.804, and that's going to be in centimeters. For this problem, we're given this f function, kx squared minus x cubed. K is a positive constant, and R is the region in the first quadrant bounded by this f graph and the x-axis. Based off of this, the first task is to find all values of k for which this area of R actually equals 2. So we're going to have to set up an expression to represent the area of R, and then we're going to have to set it equal to 2 and solve for k. So let's talk about the area of R. To figure this out, I'm going to need an integral of the f function over some interval. What interval would that be? Well, it's going to be wherever this function intersects the x-axis, because they said the area R is bounded by the graph of f and the x-axis. So I'm going to have to see where f of x basically equals 0. So we're going to set this whole thing equal to 0 and solve for x. I can start by factoring out an x squared, leaving me with k minus x, and all of that equals 0. So I see this equation is going to be true if x equals 0 or k. So now I'm going to set up an integral from 0 to k. This is going to be my area integral here. And inside I'm going to have the f of x function, which I'm going to write out just so I have a better look at it here. I'm going to put a dx there as well. And this needs to equal 2 when all is said and done. So let me use my fundamental theorem of calculus to expand and evaluate this thing. So my antiderivative, I'm going to have, let's see here, this bumps up to a 3 using my reverse power rule. So dividing by that, we've got 1/3 kx cubed. And for this next one, this bumps up to a 4. So we've got minus 1/4 x to the 4th. All of that evaluated from 0 to k. And again, all of that has to come out to 2. So I've got all of this with k plugged in for x. So this is going to be 1/3 k times k cubed minus 1/4 times k to the 4th. So that's going to be subtracted by all of this stuff with 0 plugged in. And of course, all that still equals 2. So now I have an equation that I can actually solve for k. Let me clean up this left side a little bit. Everything in the second bracket here is going to go away because you're multiplying by 0. So it's really this first bracket that's going to make the difference. So I can write this as 1/3 k to the 4th minus 1/4 k to the 4th. All of that equals 2. Let me combine these since I have the same exponent. So this is really, let's see, common denominator of 12. We've got 4/12 minus 3/12, which is 1/12, k to the fourth, equals 2. Multiplying by 12, I have k to the fourth equals 24. And now I have to take the fourth root of both sides. Now, I don't need to know exactly what the fourth root of 24 is. I can actually just write fourth root of 24 and be done. Do I need a plus or minus on this since I'm taking an even root of an equation? Normally I would, but they said that k was a positive constant, so I'm only going to take the positive root of this. So then I'm just going to write k equals positive fourth root of 24. For this part, for k greater than 0, we want to write but not evaluate an integral expression in terms of k for the volume of the solid generated when r is rotated around the x-axis. So we always have to ask ourselves, first off, it's a solid of revolution, so the area slices that we're going to be adding up to get this volume, they're either going to be discs or washers, pancakes or donuts. We have to ask which one. To figure out, we have to see if there's any kind of space between the region R and the axis of revolution. Since R is being rotated around the x-axis, and R is bounded by the graph of f and the x-axis, since the x-axis is both one of the boundaries and the axis of revolution, that means there's actually no space between R and the axis. So that means we are going to use discs rather than washers. So I'm going to set up my area formula. A of x equals pi r squared. Of course, I can't leave it like that. I have to express this in terms of x. So what's this r value going to be? Well, r is just going to be the distance from the axis of revolution to the outer edge of the boundary, which basically is given by this f of x function. So this is just pi times f of x squared. And I could write the whole function out, or I could just write f of x because they've defined it. Either one is fine. So now that I've got my area function, I'm just going to integrate this over the interval from, well, let's see, whatever the limits of integration for the area r were. Remember from part A, we found that those were 0 and k. So then I have volume equals the integral from 0 to k of, and now that I defined this, I can just write a of x dx. For this last part of the problem, they want to write but not evaluate an expression in terms of k with one or more integrals that tells us the perimeter of R. Well, R is bounded by, again, the graph of f and the x-axis. So to get the perimeter of R, we just have to add up the length of these two boundaries. So we're going to have the easy one first we'll talk about. That's going to be the x-axis. So that's just going to be our x-axis distance from 0 to k. Plus, we're going to have to add up the arc length of the function f. So to find that arc length, I'm going to have to take the derivative of f, which is going to be, let's see here, 2kx minus 3x squared. So that's f prime. And I'm going to have to use my arc length formula. And I'll do that in just a sec. So let me write now, perimeter is going to equal distance from 0 to k, which again is just going to be k, right? K minus 0. Plus, now we have to have an integral, this is the arc length formula now, integral from 0 to k of, and now I'm going to have to take the square root of 1 plus f prime squared dx. So this is just using our standard arc length formula. And this is it. This is the integral that gives us the perimeter, so we are done.